Hello everyone, my name is Farshid Varno. I'll be presenting our paper Minimizing Client Drift in Federated Learning via Adaptive Bias Estimation. Let's assume you have multiple devices that collect data and you want to train a machine learning model on this data. Traditionally, all the data should be first transferred to a device where you want to train your machine learning model. But depending on the application, this approach can have high communication and privacy costs. What if the model parameters are transferred instead of data? Well, that is how federated learning works. Local SGD is the most basic federated learning algorithm. It works iteratively as follows. At the beginning of each round, the server sends its cloud model to a random selection of devices known as clients. These copies are trained locally, then they are sent back to the server and are averaged out. The result is the cloud model of the next round. The cycle repeats until the algorithm converges. In most real-world applications, the distribution of data is not the same on all clients. So local updates deviate from those of the centralized approach. This is called client drift. Local SGD does not have a mechanism to remove this drift, so it gives a suboptimal solution. One promising technique is to combine reduced variance SGD algorithms with local SGD. The general strategy is to regularize the local updates with an estimate of gradients on other clients. For client I, this estimate can be found by subtracting an estimate of gradients of client I from an estimate of gradients of all the samples on all clients. Now let's see the algorithms that use this strategy. The scaffold directly applies the estimated gradients on local updates. However, it consumes twice as much communication bandwidth as local SGD. Feddyne addresses this communication issue, but its gradient estimates are not properly adapted during the training, which results in parameter explosion. Our proposed algorithm, AdaBest, not only addresses all these issues, but also achieves faster and better convergence. AdaBest adapts gradient estimates locally by the number of rounds in which a client is absent from training, and globally by its discounting factor beta. Beta is an extra hyperparameter to tune, but our experiments suggest that with AdaBest, other hyperparameters such as learning rate require less tuning. For example, these two plots show training on C400, that is a split on 1000 and 100 clients. All the settings, including learning rate and the number of clients per round, are kept identical. But notice that among all these algorithms, only AdaBest shows a consistent performance on both settings. Here are test accuracy scores for various datasets, task difficulties, and client participation rates. Compared to the baselines, AdaBest consistently shows superior performance. Nevertheless, the competition becomes closer for the full client participation settings. In the paper, we analytically show that for these cases, Feddyne and AdaBest become nearly identical. In summary, local SGD is subjected to client drift, making it a suboptimal solution. But it can be combined with RV-SGD algorithms to minimize the client drift. AdaBest provides such a solution, addressing the stability and efficiency problems that the prior works had. With the expense of tuning an extra hyperparameter, it can converge faster and to a better performance. Thank you very much.